Network outages are a major headache for the networking industry. They are notoriously disruptive and cost several hundred thousands of dollars. But why do? According to Microsoft, one of the largest cloud providers, 1 out of 3 major network incidents are attributed to human errors and network misconfigurations. Naturally, this has motivated a large body of work on network. This paper is about finding the right set of abstractions that will help us build compositional models of networks and of their configurations, and that will simplify the development of reusable and scalable network. To this end, we designed MV, a functional language to model network protocols and their configurations. We built highly scalable network analysis on top of these models, and we saw how you can build your own analysis just by writing programs in the MV language. So if you want to find out how you can easily code a fault tolerance analysis that outperforms the current state of the art, just come to our
Modern GPUs used in HPCs adopt ECCs to protect large register files from soft errors, but they cause high hardware overheads and energy consumption. To replace ECCs in the register files, we propose a compiler-directed resilience scheme, Penny, which combines error-detected code with idempotent recovery. For ECC, errors in register can be corrected using the additional parity bits. However, this error correction requires a high bit redundancy. Instead, Penny uses much inexpensive error-detecting code to detect errors, and the error is corrected by re-executing current idempotent region. A code is idempotent if it can be re-executed many times and still result in same output. Penny shows a useful property of not requiring an error to be corrected before the region that error occurred ends, unlike previous idempotent recoveries. To mitigate the overhead of required checkpointing, we introduced several compiler optimizations, such as moving checkpoints out of the loop and pruning checkpoints that can be reconstructed at recovery. Thanks to the optimizations, Penny's performance overhead is only 3%.
An energy harvesting device collects energy from its environment and runs opportunistically after collecting enough energy. Running a program with a periodic schedule or in response to external events is challenging on such a device because the device simply cannot operate when there is not enough energy. To run periodic and reactive programs, an energy harvesting system must schedule both code execution and recharging at the same time. Scheduling recharging is challenging because incoming power varies over time and recharging time varies with the incoming power. We present CatNap, a programming model and a runtime system that schedules both code execution and recharging, thus safely executing periodic and reactive applications correctly on an energy harvesting device. Come to my virtual talk on Wednesday, 7 a.m. Pacific Time to learn more about our work.
Every day, we use navigational tools like Google Maps to find the best route to our destination in terms of traffic. However, road closures can happen and traffic needs to be rerouted, which can lead to heavily congested roads. Real-world computer networks face similar congestion problems when links fail and traffic needs to be rerouted. Our tool called Quark can detect such violations proactively using an abstract representation of the network control plane. In the real world, we can alleviate traffic by adding more lanes. Similarly, Quark can be used to find which network links need to be upgraded in capacity to prevent congestion problems.